Today we're gonna study the magnetic field and the discovery of the electron, which is chapter 28. So first, let's start with actually what produces the magnetic field. What produces the magnetic field is a moving charge. If a charge, let's see, for example, you have some proton, and this proton move with certain velocity v, okay? This proton will generate a magnetic field. Let's see, for example, if you have some wire. Here is a wire, and then you have some current going this way. Here is the current I, and the electrons are going the opposite way. These are the electrons going the opposite way. So the current I is going to the right. So this motion of electrons here produce magnetic field. So it's easy to know the location of the magnetic field. It's easy is because all you have to do is grab the wire, grab it like this with your hand, and make sure your thumb is pointing in the direction of the current, like this. And let's see, this is the wire, is the pen, and I'm gonna grab the wire and my thumb going, following the direction of the current like that. And then look at my fingers here. In this location, at the top, my fingers are coming out. So the magnetic field is coming out. So I put a dot, so this is the B field. And now, if I keep, remember my thumb has to always point in the direction of the current. So it's going like this. Look at now my fingers. At this location here on the paper, my fingers will go down like that. You see they're going down? So the magnetic field at this location is going into the paper. So, and then the magnetic field actually is circling. So it's going like that, circling. Now, there are a bunch of magnetic fields, a bunch of them, magnetic field lines. So as you move away from the wire, let's see, this is R. As you move away, so a certain distance R, let's see if R becomes big, then the magnetic field will become small. So what makes this, what creates this magnetic field is the motion of the particles, or of the charged particles. Now, there is another situation also when you have some magnet. Let's see, this is a magnet. If you take any magnet, it has north and south, two poles. Now, these magnets is made of material, and those materials are made of atoms and electrons, protons, neutrons. And you see these particles, they move, and some of them are charged, like the proton and the electron, they are charged. So, for example, the electron is charged and is going around, moving, so it's going to generate a magnetic field. So what happened for a magnet, this magnet has this thing called magnetic moment, which is a characteristic of a moving or spinning charge. And what happened, these moving charges, they create magnetic field. And because there's so many of them and they're pointing in the same direction, then the magnetic field will be pointing, like, will, for example, come out of the north like this, and then will go to the south, like that. So those moving particles that inside here, moving charged particles, creates this magnetic field. Now, if you take this magnet and cut it in half like that, when you cut it in half, you're going to generate two magnets. You'll have one here, okay, which has north-south, and then you have one here, north-south. So you always have two poles. If you cut, let's see, this magnet in half like that, then you have again north-south, north-south. So you keep going all the way to, if we go, for example, all the way to the electron. The electron is a charge and has a spin. So it has a magnetic moment called mu. So the electron itself has a magnetic moment, and you can see that it's very hard to cut the electron in half. So it's very hard to, it's actually impossible so far physically to have one monopole. Like for example, the charge, the electric charge you can have one charge like Q. You can have a dipole like plus Q minus Q. So this is a dipole, plus Q minus Q. And then you can see you can cut in half and then get one pole here, one pole separately. But you can't do that with the magnet. You cannot do that with the magnet. If you cut in half, you'll get north-south, north-south. So there is no monopole for a magnetic field, but there is a monopole in electric field. So this magnetic field, it exists physically. To see it, you can just take, for example, some piece of paper, okay, and on that piece of paper, dump some dirt from the ground, put dirt here from the ground, and underneath that paper put some magnets. If you look at it from the side, I have a magnet here, and here you have a bunch of dirt. And then you flip the paper, so when you flip the paper, so the dirt is here, and the magnet is up here. Now when you flip the paper, the dirt will fall off, and then the pieces of metal will stay there because they're attracted by the magnet. And this piece of metal, you can move them. You can move the magnet underneath the paper, and you can see actually the field lines. These small particles of metal on the paper will move in certain direction following the field lines of the magnetic field. Now, well, like I said, this magnetic field exists physically. It's not a mathematical thing. It's actually a physical thing that exists. Now you can look at the effect of the magnetic field on an electron, and a scientist by the name Thomson, I think, this guy, he took an electron like this, and then he generated some difference of potential. So you have here some, let's see, for example, this is a positive potential, this is negative potential. So you have a difference of potential delta V. And then he took like some wire, heated up wire, and then you have some hole here. When the wire gets so hot, these electrons here get attracted by the electric field that's inside in between here, because once, let's see, for example, you can do something like that. You put like voltage here and voltage there, and then you have these electrons moving in this thin wire. So the wire gets so hot, and those particles there, or the electrons, they're moving and they're about to leave because it's too much heat. So once you put some difference of potential, you attract them, so they come out. And then when they come out, they get attracted by these difference of potential. There is an energy actually, which delta U is equal to the charge of the electron minus E, and then times the difference of potential. This is the potential energy, this is the potential, and this is the charge of the electron. So you have some energy here that works on the electron and make it go fast. So the electron will come out, and then if you put two plates, so did J. Thomson, he put two plates like that. One plate is positive, okay, and one plate is negative. And this electron will come out like that, and then it will enter this region between the two plates. And you can see here we have an electric field. The electric field always goes from the positive to the negative. So we have an electric field. So the electron will try to go to the positive side, so it will go up like this. And then here he put a screen. So you can actually look at the deflection. You can calculate this deflection Y. this deflection y that the electron made as it goes up, because it's attracted by the electric field between these two plates. Now, one thing we need to know, let me make the plate go all the way here to the screen. This plate here, go all the way to the screen, like that. Now, this distance, we can call it L. This is L. So this electron that enters this region between the two plates, this electron enter the region, what happened is there is no force acting on it in the x direction. There is no force because it's just moving, like it got pushed by this difference of potential and it's moving because of that push. Now there is no force. So the velocity along this L is constant. So you can use this equation. L is equal to the velocity times time. And the time to go from, let's see, from point A to point B. This is the time to go from here to there. Now, this electron, the reason it goes up like that, it moves up like that, is because there is a force. There is an electric field here, and you know that the force is equal to QE. This is the force is equal to QE. So we have the force is equal to minus E, and then the reason I put minus E because the electron charge is negative. So you can see the electric field is pointing down. Look at here, the electric field is pointing down, and then you have a negative sign. So it means that force is pointing up. So the force will be pointing up like that. The force is pointing up. So that's why the electron goes up. So it has this force. In magnitude, we just put here, that's the force, Fe. Now, we can find the acceleration of the electron as it moves up from the negative to the positive. We apply Newton's law. Ma is equal to Ma. Let me go up here. Ma is equal to E times the electric field, charge times the electric field. And you can see here that the acceleration is equal to E over M. What we try to do here, we try to find this displacement y. We need to know by how much these electrons got displaced. So here is the acceleration. You can see that the acceleration is constant. This E is constant, capital E is constant, the mass of the electron is constant. So we can apply kinematics. We can apply this equation. Y is equal to 1/2 AT squared plus V0 YT plus Y0. Now, we don't have a velocity, initial velocity in the y direction, because if we started from here, the electron doesn't have a velocity in the y direction. So this one is 0. We can also say at time t equal to 0, we can choose this as our origin in the y direction. We choose here. So at time t equal to 0, the electron is here, is at 0 location. So we can do that. And then we have this y is equal to 1/2 AT squared. Becomes simple. Now, A, we have it, it's here. That's the acceleration. So we can write, I can write y is equal to 1/2 A. I put here E over M and then T squared. Here is one equation. Now the problem is that T, we can find T actually. It's easy to find T. If you know the distance and you know the velocity, you can find T. Look at T is here. T is there. Let's take T from here. So T is equal to L over V. Now we take this T here, this T, we take that T and plug it here. So we have y is equal to 1/2 E, and then times the electric field over M. And here we have L squared over V squared. Okay, So you can see here that that's why we can actually find y. And here is the problem. The problem is this. We don't know the velocity. Look at L. L, we know, is just the length of the plate here. The electric field, remember, J.J. Thomson is the one who produced the electric field for this experiment, so he knows E. The mass of the electron, the charge, these two, at that time when J.J. Thomson did this experiment, he didn't know the mass of the electron and he didn't know the electron. He didn't know them. But this velocity, you can actually find the velocity. How do you find the velocity? We have the follow me here carefully because this you need thinking. We have this material needs thinking. We have an electric force going up. So which is, where is it? Is this one. That force is going up. Now if we put a magnetic field, let's see if we put a magnetic field, and that magnetic field, let's see, is pointing down like this. Okay, it's pointing down. It's going like that between the plates. And this magnetic field B is going into the paper. What will this magnetic field do? It will generate a force because remember, this electron is moving in the magnetic field B. So a force is going to be generated. And that force here, F, is equal to QV cross B. That's the force. Now, if we look at just the magnitude of the force, we put here F is equal to EVB. Now, look at here, the velocity is going to the right. Look at the B field, is going into the paper. So they're perpendicular. So I don't have to use sine theta between V. Sine theta between V and B is just 1 because the angle between V and B is pi over 2. So sine theta is just 1. So the force will be just EVB. So we have a force. Now we need to know the direction of that force. Remember, the electric force is going up. Now, the magnetic force, we need to do the right-hand rule to find the magnetic force. So what I'm going to do, I'll come over here in this location here, and try to find the force at this location. So the electron is going this way. So this is the velocity of the electron. The magnetic field is going into the paper. Now, I'm going to use the right-hand rule. Look at V is going to the right. So my fingers will go to the right. The B field, okay, the B field is going into the paper. Here is the B field going into the paper. So I go this way, okay? I don't know if you can see. My fingers are following the velocity like that. The B field is into the paper. So my fingers, the palm of my hand needs to point into the B field. So, and I need to rotate my fingers in towards the B field. As I rotate my finger, look at my thumb. My thumb is going up. Now, hold on. With the force, because remember, we have F is equal to minus, if I don't use magnitude, I have F is equal to minus EVB. I have a minus sign here because it's an electron. So the force actually, because of this electron, is going to flip and come down. So you have a force that's going to come down. Magnetic force that will oppose the electric force, go this way. So this is FB. And remember, this is the FE. Okay? So here, if I come to this location, we have FE. Here is FE. And here is FB. So, I'm sorry. This is FB, is pointing down, and this is FE. from here. Fe is pointing up and Fp is pointing down. And the electron is here, moving. And these two forces acting on it. Now, what this J.J. Thomson did, he tuned the B field as the electron. He tuned the B field so that this force is equal to that force. So the electron is supposed to go up because of the electric field. But if there is a magnetic field force, there is going to pull the electron down. So you have these two forces competing for the electron. The electric force tried to push it up, and the magnetic force tried to pull it down. And these two forces he tuned. Remember, he can control the B field that's generated here. He can control it. And he can control the electric field. So he kind of tuned this electric field and magnetic field, tuned them out so that the two forces are equal to each other. Now, if the forces are equal to each other, we can do this. This equation here, I have this one and this one. Let me use the magnitude. F is equal to EVB. This force and this, those are equal to each other. You can tune it, and once the electron align, and you no longer have that Y that he found, this Y that he found before, he no longer has it. So what he did, he made this force equal to that one, and in the equation, you're gonna have EVB is equal to E. Cancel small e, and then you have the V is equal to B E over B. And look, now he found the velocity. Now the crazy thing is this paper, I ran out of room. He took this velocity and put it there. Put it there, the velocity, put it there. Now let's see what's going to happen if he puts it there. So I need to go down up here. I have some room here. Okay, I have some room here. There. And I'm going to take Y. I put here Y is this here. This. And I'm going to replace that into there for V. So I have Y is equal to 1/2 E, capital E, the electric field, over M, L squared. And then here, I put V squared, which is E squared. And here, B squared. Look what happened to E. E cancels one of them. So I have now E, L squared, B squared, over 2M, and then E, and this is Y. Now, this J.J. Thomson guy, this one, this guy, what he was looking for is this ratio M over E. That's what he was looking for. So let's see if we can do that. So we have M over E is equal to M over E, L squared, B squared over 2YE. You see, M over E, look, M over E is equal to L squared, B squared, 2YE. Now what happened, this J.J. Thomson is a nice story. He got stuck because he was looking for the mass of the electron or the charge of the electron, but he found the ratio. He doesn't know. He didn't know the mass of the electron. He didn't know the charge of the electron. Now, but he knows the ratio. So he has to wait 10 years for, actually this J.J. Thomson was a British scientist. He has to wait for an American scientist called Millikan. I think maybe two L's, I'm sorry, Millikan. This scientist, he made another experiment. He found the charge of the electron. Once he found the charge, J.J. Thomson, because he has the ratio, he found the mass. Okay? So now this happened, this J.J. Thomson, he did this experiment in 1897. So in 1897, people didn't know the charge of the electron, the mass of the electron. And they have to wait 10 years. And then after 10 years, then they start knowing the charge and the mass of the electron. And how did this come about? Is by knowing the force that acts on the magnetic force that acts on the electron, which is this force here, and the electric force that acts on the electron, which is this one. So this combination of these two forces gave us this. Okay. See you guys.